Greetings and welcome back. Kamal here, your friendly neighborhood integral solver, and today we're going to be solving the integral from negative to positive 1 of... Oh my god, you guys have some serious issues if you're watching this video right now. But it's fine, we're all sickos here anyway. So we might as well go through it. This is Cleo's most famous integral. Cleo, the math genius from Math Stack Exchange, who just posts the answer to a very tough integral, then disappears. And I am, to this day, still surprised that this thing even has a closed form. This is awesome. This is an absolute beast of an integral. Our solution development is going to make use of some symmetry, followed by Feynman's trick of differentiating under the integral sign. So it is a beautiful solution development, and it's going to involve some beautiful complex analysis later. So here we go. Enough talk. What are we trying to do? Like I said, we're going to invoke some symmetry. So we're integrating from negative to positive 1, so we might as well try what happens when we take x to the negative x world. That takes dx to negative dx. So I is now the integral from positive 1 to negative 1 of negative 1 by x times root 1 minus x divided by 1 plus x times the logarithm of 2x squared minus 2x plus 1 divided by 2x squared plus 2x plus 1, and we have another negative sign with the dx. The two negatives do cancel out, but the limits look kind of weird, so we switch them up. So we have the integral from negative to positive 1, terribly sorry about that, of 1 by x times root 1 minus x, again terribly sorry about that, divided by 1 plus x times the logarithm of 2x squared minus 2x plus 1 divided by 2x squared plus 2x plus 1 dx. Okay, cool. Oh, the negative sign because of the switch up of limits. Now, one more thing to note here is that we have the log of something. Now, log 1 by z equals negative log z. So this implies that we can write I here as the integral from negative to positive 1 of 1 by x times root 1 minus x divided by 1 plus x times the logarithm of 2x squared plus 2x plus 1 divided by 2x squared minus 2x plus 1, where the negatives cancel out, of course. Okay, cool. So if we take a look at this structure and the structure of the integral that we started with, we see it's exactly the same. In fact, I'm just going to copy this down so we can have a view of these two together. And there we go. So there is no difference barring the root 1 minus x over 1 plus x term. So let's add up these integrals to get on the left-hand side 2 times I, and on the right, using the linearity of the integration operator, we combine them to get, well, we have 1 by x times log 2x squared plus 2x plus 1 divided by 2x squared minus 2x plus 1 factored out. And we're left with what exactly? We're left with root 1 minus x divided by 1 plus x plus root 1 plus x divided by 1 minus x dx. And this is pretty cool because it's very easy to simplify. This thing here is just going to be, well, 1 minus x in the square root squared plus root 1 plus x squared divided by root 1 minus x times 1 plus x, which of course yields on simplification. We also see the x's will cancel out, so there we go. So we have a factor of 2 here, and in the denominator we have 1 minus x squared. Okay, cool. And the 2 over here canceled out quite nicely with the 2 out there. So this means that I is in fact the integral from negative to positive 1 of 1 by x times root 1 minus x squared times the logarithm, again terribly sorry about that, of 2x squared plus 2x plus 1 divided by 2x squared minus 2x plus 1 dx. Now it looks like we could make a nice substitution here, and that is letting x here equal sine of t, which implies that dx equals cosine t. And by that token, we have I equal to, as x tends to -1, we need t to approach negative pi by 2. And so we have positive pi by 2 up here, 1 by sine of t, and root 1 minus sine squared t, which is, of course, the cosine function. So we have cosine t times the logarithm of what exactly? We have 2 sine squared t plus 2 sine t plus 1 divided by 2 sine squared t minus 2 sine t plus 1. Wow, this really is something, and I need some more writing space to write the integrand of this single integral. So dx transformed into, sorry about that, cosine t dt. So we have some lovely cancellation taking place. And so we have I equal to the integral from negative to positive pi by 2 of 1 by sine t times the logarithm of 2 sine squared t plus 2 sine t plus 1 divided by 2 sine squared t minus 2 sine t plus 1 dt. Okay, cool. We've definitely done something. We've transformed the integral into a form that is slightly, only slightly more hospitable than the structure we started with, but it's still something that if you show it to your calculus teacher, he's gonna say, dude, you need help. And if you show it to some random people walking down the street, they're probably gonna call the cops on you. But anyway, what's important here is that we need a way of solving the integral. Well, one big hurdle for me here is the fact that I have to keep reading out the argument of this log function. But we notice something about it. We notice that we have similar looking quadratic polynomials in sine of t upstairs and downstairs. And we could do with a factorization. So if I take the function 2 sine squared t minus 2 sine t plus 1 and set it equal to 0 and solve the equation so I get the roots, that means that sine t equals good old quadratic formula 2 plus or minus root 4 minus 8 divided by 2, which equals 2 plus or minus 2i divided by 2, which means that the roots of the equation are 1 plus and minus I. Okay, cool. That means we have a factorization. We do need a 1, so we start at 1, and we have minus alpha times sine t, where alpha is the first root, and then we have 1 minus beta times sine t. So we have alpha equal to 1 plus I, and beta is 1 minus I, which is just, of course, the complex conjugate of alpha. And if you factorize, rather, the polynomial upstairs, you'll find that the roots of the corresponding equation are in fact the negatives of the roots of this equation. Okay, that is actually very, very convenient, because now we're going to define an integral function. We have I of some parameter alpha defined as the integral from negative to positive pi by 2. And we did have a 1 by sine t there, and I'm just going to rename the dummy variable back to x. And we need the logarithm of 1 minus alpha sine x dx. This is actually quite useful. Now we differentiate with respect to the parameter alpha, giving us on the left-hand side I prime of alpha. And on the right, after switching up the order of the integration and differentiation operators, we have the integral of the partial derivative with respect to alpha of 1 by sine x times log 1 minus alpha sine x dx. Now, because the sine function is a constant here for differentiation purposes, we have the integral from negative to positive pi by 2 of 1 by sine x, and differentiating the logarithm gives us 1 minus alpha sine x. And by the chain rule, we have negative sine x up here. Some nice cancellation. So we have negative integral negative to positive pi by 2 of dx divided by 1 minus alpha sine x, which is quite nice because this is a standard sort of integral we can solve using the Weierstrass substitution. So we'll just let tangent x by 2 equal t, which implies a lot of stuff. First up, we do need a right angle triangle, so pretty cool. So the acute angle here is x by 2. We have t here as the perpendicular. The base is 1. So the hypotenuse is 1 plus t squared, root 1 plus t squared, that is. So we can get the sine and the cosine functions of x by 2. Sine x by 2 is t divided by root 1 plus t squared. Sorry about that. And cosine x by 2 is 1 divided by root 1 plus t squared. Now we need the sine of x. So sine x by the double angle formula equals 2 sine x by 2 times cosine x by 2. So that means we're just left with 2t divided by 1 plus t squared, which is quite nice. Now what about the differential element? Well, tangent x by 2 equals t, and this means that 1/2 of secant square x by 2 dx equals dt, and this further implies that dx is just 2 dt divided by secant square x by 2, and from the cosine function we see that that should just be, well, we have secant square downstairs, so that's just cosine square x by 2 dx, and that of course gives us 1 by, so we have 2 by 1 plus t squared. Sorry about that, there's a dt here. Much better. So those are all the transformations done and dusted with. Now the integral I prime of alpha equals the integral from, so our limits were negative to positive pi by 2. So tangent x by 2 approaches tangent pi by 4. So we have negative 1 and positive 1. Our differential element is 2 by 1 plus t squared dt. Then downstairs we have 1 minus alpha sine x, and alpha sine x was of course this thing. So we have 1 minus 2 alpha t divided by 1 plus t squared. And we can expand upstairs and downstairs by 1 plus t squared, giving us negative integral negative to positive 1. We have a negative 2 out here rather. And we have dt divided by 1 plus t squared minus 2 alpha t, which looks pretty cool. And we can actually complete the square in the denominator. So with that strategy, we have negative 2 integral negative to positive 1 dt divided by 1 plus, we got t squared minus 2 alpha t, so we do need an alpha squared term here, plus alpha squared, so we have 1 minus alpha squared, and this means we have negative 2 times integral negative 2 positive 1 dt, and we have t minus alpha whole thing squared plus 1 minus alpha squared. And yes, indeed, this does look like an inverse tangent integral. So we're going to let t minus alpha equal root 1 minus alpha squared tangent theta. And this means that dt equals root 1 minus alpha squared secant square theta d theta. And what about the limits? Well, we have this thing, which means that tangent theta equals t minus, or we can write this as theta equals inverse tangent t minus alpha divided by root 1 minus alpha squared. So by that token, we know that t approaches negative and positive 1. So as t approaches negative 1, we have theta approaching the inverse tangent of negative 1 minus alpha. We can factor out the negative sign, inverse tangent being an odd function. We have it outside. We have 1 plus alpha divided by root 1 minus alpha squared. And 1 minus alpha squared is 1 plus alpha times 1 minus alpha. So we have some further simplification. It's inverse tangent root 1 plus alpha. I'm going to need some writing space to actually write that thing clearly. So we have root 1 plus alpha divided by 1 minus alpha. And similarly, as t approaches 1, we have theta approaching the inverse tangent of its t minus alpha. So we have 1 minus alpha divided by root 1 minus alpha squared, and this equals the inverse tangent of root 1 minus alpha divided by 1 plus alpha. Okay, cool. So this implies that the derivative of I with respect to alpha, I probably should have copied it down. Where did it go? Okay, it's right over here. Just going to copy this down. I was probably going to forget the negative sign anyway, so still. Gotta be careful. We got negative 2 times the integral, with the limits being those inverse tangents. Inverse tangent of, wait, I might need some more room. So inverse tangent root 1 plus alpha by 1 minus alpha, inverse tangent root 1 minus alpha by 1 plus alpha. Terribly sorry about that. Much better. And for the integrand, we had root 1 minus alpha squared secant square theta d theta. And down here, because we have, oh, here it is, because we have something squared, well, this is tangent squared times something, that something being 1 minus alpha squared, which we factor out. And then we're left with tangent square theta plus 1. Of course, we have cancellation here because the denominator tangent square plus 1 is secant square. And again, we have some further cancellation because of root 1 minus alpha squared and 1 minus alpha squared itself. And this implies that I prime of alpha equals negative 2 divided by root 1 minus alpha squared. And we just need the limits now. So we have inverse tangent of root 1 minus alpha divided by 1 plus alpha, 2 negatives canceling out, inverse tangent of root 1 plus alpha divided by 1 minus alpha. And now we just have inverse tangent of something plus the inverse tangent of the reciprocal of that something, and this is supposed to equal pi by 2, which is again very convenient. And this implies that I prime of alpha equals negative pi divided by root 1 minus alpha squared. Our next target is to recover back the integral function by integrating with respect to alpha. Terribly sorry about that. There we go, much better. So that means on the left we have I of alpha, and we have negative pi times, this is just the antiderivative for the inverse sine of alpha. So we have inverse sine alpha plus a constant of integration c that we now need to determine, which is again quite easy. Because we defined I of alpha as the integral from negative to positive pi by 2 of log 1 minus alpha sine x divided by sine x dx. So if we take alpha equal to 0, we have log 1, which is 0, so the entire integral just collapses to 0. So we have I of alpha, I of 0 equal to 0. And using this information, we have 0 equal to negative pi times arc sine 0 plus c, implying that c here equals 0, which is again very convenient. And before we proceed with our solution development, huge shout out to mathematician Rizwan Khalezme. I hope I did not butcher his name. I'm pretty sure I got the first name right. And his Instagram handle is Rizzy, aka MathBay, and this guy's Instagram page is goated. It is amazing. I mean, if you like my channel, you're gonna love his content. Absolutely love it, because you have a lot of stuff that I do, like special functions, Feynman's trick, or cool integration techniques, cool integrals, differential equations, some analytic number theory as well. But he's just much, much better than me. I mean, he's goated. This guy's awesome. He also solved Cleo's integral using Feynman's trick, but his approach was a bit different than mine. It was rather more generalized as well, because he found a couple of cool integration results along the way as well for, you know, related integrals as well. And that's the thing with him. Even when I find a result, after doing some digging, I find out that he's already derived that way before I did, along with some generalized and related cases, which is extremely cool. So for math education content, brilliant page on Instagram. Highly recommend that you go to Instagram and just smash that follow button. You literally have to smash it. It is worth smashing your phone just to get a follow, and then you can get a new phone. But in the new phone, you've already, once you've logged into Instagram, you're already following him. So yeah, there are benefits. Anyway, fact of the matter is, absolutely amazing educational content. And I've linked his account along with his solution development of Cleo's integral in the description box. So do drop him a follow by, smashing your phone, and also drop me a follow. There are a couple of ways you can do this. First, you will go to Instagram and then you follow me. Then you head over to Rizzy's account and then you smash your phone to follow him. Or you could first smash your phone by following Rizzy's page, and then on your new phone you will follow me on Instagram. So there are two ways you can go about this. Either case, your new phone will be packed with a couple of really cool math pages. So I guess it's a win, technically speaking. Back to work. We have this result, and this is actually wonderful. It's brilliant. The reason for that is that the target integral was in fact the integral from negative to positive pi by 2. Terribly sorry about that. Of 1 by sine x times the logarithm of, let's see, we should have 1 minus alpha sine x in the denominator. And on the right hand side, that would actually translate to having positive inverse sine alpha, because then you would have negative signs on both sides. And of course we need a 1 minus beta sine x as well. So that's something added to it. So we have plus pi times, we just factor out the pi, we have inverse sine of beta. Okay, cool. That is quite nice. And recall that for our case, the roots of the quadratic upstairs were negatives of the roots of the quadratic downstairs. So upstairs we have the factorization 1 plus beta sine x times 1 plus alpha sine x. And what does this mean for the result we have? Well, if we replace alpha by negative alpha, then we have 1 plus alpha here, and then we have negative pi times inverse sine, I wrote that wrong, inverse sine of negative alpha here. And that of course means we have pi times the inverse sine of alpha. Okay, cool. That is really nice because we already have inverse sine alpha and inverse sine beta, so that means all we need is a factor of 2. So let me just switch back to blue color. Then we have 2 pi inverse sine alpha plus inverse sine beta. Very nice. This is extremely cool because now we know that for the target integral I, we just need 2 pi times the inverse sine of alpha being equal to 1 plus I, and then we need the inverse sine of beta equal to 1 minus I. And now for some complex analysis. Now you could just raw dog this by using the definition of the inverse sine function from complex analysis, or we could have some more fun and analyze the fact that we have the inverse sine of a complex number z plus the inverse sine of its complex conjugate, which is of course really cool. So we have inverse sine of some complex number a plus I times b equal to another complex number x plus I times y. And that means a plus I times b is actually the sine of x plus iy, and we can expand this. We have sine x times cosine iy plus the cosine of x times the sine of iy. Now cosine iy is just the cosh of y, the hyperbolic cosine that is, so we have sine x cosh y. Now sine of I times y is the hyperbolic sine or sinh of y times I, so we have I times cosine x times sinh of y. Terribly sorry about that again. Slightly better. So that's a plus I times b. Now if we take the complex conjugate, then we have, again terribly sorry about that, a minus I times b equal to sine x times cosh y minus I times cosine x times sinh y. And that means that we have sine of x minus I times y. Yes, indeed. And this means that x minus I times y equals the inverse sine of a minus I times b, which is a very beautiful result because it means that the inverse sine of the complex conjugate is just the complex conjugate of the inverse sine of z. Absolutely beautiful. And that is indeed quite remarkable, because that means when we add them up together, we get twice the real part of inverse sine z, and we called the inverse sine of z's real part x here, so that's okay. So all we need is 2 times x. So our strategy will be to evaluate the inverse sine of 1 plus I, and then take out its real part, and then just double it. That's our strategy. Now the inverse sine function has this really cool principal log form, which is what we're going to make use of. So we have I times z, and iz here is just I times 1 plus I. So that would be I minus 1 for our case. Z equal to, wait, over here, z equal to 1 plus I. And what about 1 minus z squared? Well, z squared would be 1 plus I squared plus 2i, and these two cancel out, so that's 2i here. And 1 minus z squared in the square root would be root 1 minus 2i. And we can write this a lot nicer in the polar form, so that way we would have root 5 times e to the negative I times inverse tangent 2. So that means, expanding this using Euler's formula, we have root 5 times cosine of inverse tangent of 2 by 2 plus, no wait, minus I times root 5 times the sine of the inverse tangent of 2 by 2. And we can actually simplify these cosines and sines quite nicely. If we analyze inverse tangent 2, letting it equal to theta, and you can do the thing with the right triangle and all that, so we have tangent theta equal to 2, and this implies that sine theta would in fact be 2 by root 5, and we have cosine theta equal to 1 by root 5. But we're not exactly interested in sine theta and cosine theta, we're interested in sine theta by 2. That would be the sine of inverse tangent 2 by 2. So sine theta by 2 is root 1 minus cosine theta by 2, and cosine theta by 2, that just looked weird, equals the cosine of the inverse tangent of 2 by 2, and that equals root 1 plus cosine theta, terribly sorry about that, cosine theta by 2. And using the value of cosine theta that we have, we see that sine of inverse tangent 2 by 2 in fact equals root 5 minus 1 divided by 2 times root 5. And the cosine of arctangent 2 by 2 equals, wait, I'm gonna need a bit more writing space. So we have root 5 plus 1 divided by 2 times root 5. And yes, you're right, the golden ratio is here. So we know that 1 plus root 5 by 2 equals phi. So the cosine term over there is just, well, root phi divided by root 5. And what about root 5 minus 1 divided by 2? This thing is root 5 plus 1 divided by 2 minus 1, correct? So that would just be phi minus 1. And what exactly is phi minus 1? We know that phi squared minus phi minus 1 equals 0, implying that expanding by 1 by phi, we have phi minus 1 by phi equal to 0. And this further implies that phi minus 1 equals 1 by phi, which is again quite nice. So the sine function here, I've run out of writing space, I'm just going to rewrite everything down here because it looks really cool. Cosine arctangent 2 by 2 equals what exactly? Oh yeah, the square root of phi divided by root 5, and the sine of arctangent 2 by 2 equals root 1 divided by phi times root 5. And this is what we have for the inverse sine of 1 plus I after plugging in the numbers and of course canceling out the root 5s. Root 5, that is. And now what? Well, we needed the real part of the inverse sine of 1 plus I. And recall for the principal logarithm of a complex number z, this equals log absolute value z plus I times the principal argument of that z, which implies that the real part of negative I times log z equals, well, I squared would be -1, negative I squared is +1, so that means we just need the principal argument of z, and z in this case is all of this stuff. So this implies that the real part of the inverse sine of 1 plus I equals the inverse tangent of, let's see, the imaginary part is it's root 1 by phi minus 1, correct? So that's just 1 by root phi minus 1 divided by the real part is just root phi minus 1, which looks, no, wait, yep, it's exactly that. It's exactly that. I actually wrote the imaginary part wrong. It's negative sign here and a plus sign over here. Much better. Now everything's making sense. We have inverse tangent of, on simplifying, we have -1 plus root phi divided by root phi times 1 by -1 plus root phi. Again, we have some lovely cancellation. So this thing equals the inverse tangent of 1 by root phi, which is, of course, the inverse cotangent of root phi. That's the real part of the inverse sine of 1 plus I, which itself is a beautiful result. But we're interested in twice its result, and for the result of our integral, we actually have to, if I remember correctly, yes, multiply it by 2 pi. So that means I here equals 4 pi times the inverse cotangent of root golden ratio, which is absolutely gorgeous. I hope you enjoyed the video. Be sure to like and subscribe. Do remember to drop me a follow on Instagram and check out Rizzy's page. And if you like the effort I'm putting into my work, you feel like I'm doing some kind of a good job, consider supporting me on Patreon. All links are in the description box. Thank you. See you next time.